It's my honor today to introduce our speaker, Dr. Zili Wu from Oak Ridge National Laboratory. Zili got his PhD at Dalian Institute in 2001. He's at the Dalian Institute. He was at the Chemical Physics Institute, which is one of the premier institutes for physical chemistry and chemical physics in China. He then went to Spain for a while. He went abroad to study. He went to Spain for a while and then came to the United States, where he went to Northwestern University and worked with Peter Stair for 3 years, developing Raman techniques for looking at surface species and molecular species on the surfaces. He then came to Oak Ridge National Laboratories, where he had a joint appointment in the Chemical Sciences Division and in the Center for Nanophase Material Sciences. He's joined the surface chemistry and catalysis group there and is still a member there until he ascended to the level of group leader in 2016. His work has been in understanding kinetics and structure of molecular species on surfaces, at least in the past, and he's moving in new directions now. He has recently got one of the DOE Earthshot Research Centers project, and he's been a thrust leader on one of the Energy Frontier Research Centers, the UNCAGE one, jointly with Georgia Tech Institute. Zili won the 2023 ORNL Outstanding Research Team Award, and in 2020, the ORNL CNMS Outstanding S&T Accomplishment Award. 2019, the Excellence in Catalysis Award from the Catalysis Society of Metropolitan New York. And today he's going to tell us about closing the carbon cycle and decarbonization in chemical reactions by thermocatalysis and electrification. Zili.
Thank you very much, Steve. Hope you guys can hear me okay. I'm trying to speak loud. Let me pull up my slide. Okay. Let's turn off and then we'll go back. All right, it's really great pleasure to be here to talk all our friends, you all being ORL. I hope from this talk you can learn a little bit more on what's going on at ORL, just in capacity field. And before I doing that, Steve told me that this is a broad audience. I'd like to briefly tell you what is catalysis. I think everybody knows what catalyze is there on that flag. So catalysis really is, think about taking reactants from point A to point B. Without a catalyst, this is the barrier you need to climb very high, typically. With a catalyst, it can absorb your molecule and then go through some intermediate state, and then you absorb species, and then you dissolve it from your product. Clearly, the pathway, the barrier is much lower. So you can think about this as you're climbing a mountain. If you want to go through one point to another point, say over the top to another point, you can go, climb all the way to the top and then go down. Or if you have a local guide where is a catalyst, you can go through the secret route, multi-energy efficient route, to where you want to go. So that's what catalyst is doing. Essentially, it won't change the dynamics, only change the kinetics. So it actually makes more energy efficient, and this really contributes to a lot of decarbonization. All right, so let me just briefly tell you about catalysis efforts at ORL. Currently, there are 3 catalysis research groups. First 2 are pretty much from one group break up, split up into about before pandemic time. Used led by Jim Parks. Most of you guys probably know him. Right now, first group is a chemical process scale-up group led by Andy Sutton, focused mostly on bioenergy, biomass conversion, and CO2 capture and conversion. The second group on the applied side, applied catalysis emission research group. It was led by George Peel. He just recently moved up to division director. So I think I'm still looking for a group leader position. As by the name, you can tell they worked very heavily on emission catalysis. But with the transition to EV cars, the funding in the emission area drops very significantly. So they are moving more to fuel cell, hydrogen production, those kind of area. Surface chemistry class group is more on the fundamental side. We are looking at C1 chemistry and also some larger molecule like plastic upcycling. I think there's one previous talk a few months back on this polymer cycling. So I'm doing more focus on C1 chemistry. So this is a current group of surface chemistry and catalysis. Very briefly, just give you a face value of a small group overall. We have about 5 staff, and you can see Stu used to lead this group. And we have this is 5 or 6 postdocs, about 10 people in the group. And the research projects mostly funded by Department of Energy, Basic Energy Science. We work on 3 major projects. One on the top is our regular BES catalyzed FWT. This one focuses on CO2 conversion using either molecular hydrogen or using hydrogen-rich molecules like methane to convert CO2 to mostly like to coupling products. So what I'm starting to tell you about today is on this project. The other project Steve mentioned is NKTB EFRC, led out by Georgia Tech. It shows in the middle panel here. Really is looking at how contaminants from real feed in the chemical conversion impact the material structure and the performance. Specifically, we're right now working on CO2 electrochemical reduction, how the captured CO2, the impurity like SOx and NOx, will impact the catalyst stability and the catalytic activity and selectivity. The third one at the bottom is Energy Earthstar Center, which I'm going to spend my second time talk about it. Is really using a non-invasive approach to drive chemical reactions. All right, so that's a little bit about the catalysis effort and the group. Now let's get to the main topic. I don't think I need to really motivate with this group. What's the real big challenge globally we are facing, the climate change. And showing here is the global CO2 emission in gigaton per year versus the timeline, of course, we're looking at. And then on the right side is projected temperature increase. So if you're doing business not in euro, not doing much, this is a gray, that's where you're expecting. So for net zero, really, that's 1.5 degrees C, that's the goal, increase. So that's where you really need to follow this, this line. So you can see we're about here, and the turning point. Really, we need to do something dramatic, very dramatic, to reach the goal of net zero by 2050 or 2100. Right now, the US goal, of course, 2050. So you need to reduce in the coming years. If you look at it, you need to reduce 50% by 2030, which is about 5 years ago. 5 years to go. That's very significant. And then you need zero emission, net zero emission by 2050. All right, so chemical industry is a big problem maker in this case. So it makes a lot of CO2 emission and consumes a lot of energy. So if you look at this pie chart on the left, industry account about 30% of CO2 emission in the US. And then chemical industry is about close to 40% of those CO2 emission. Energy consumption-wise, similar. 30% industry and 40% the chemical industry. And also this expecting keep increasing by 25% 2050. So we definitely need to do something to really help to reach the net zero goal in chemical industry. So what are pathways you can go there? So here shows the gray bar. That's essentially what we're doing now. And those different color bar, that's the ways that you can help to decrease the CO2 emission. This including CCUS, that's basically carbon capture utilization. Then the blue one is industry electrification. The yellow one is energy efficiency improvement. And then the purple one is alternative products. So adding all this toolbox together, you can potentially reach net zero. So the alternative approach, including so-called, you heard about DAC, direct air capture, also called electric carbon technology. So all those actually has been practiced at some certain level, but to reach that, we only have 2.5 decades to go. That's a daunting challenge there. So what I'm going to show you here today is two cases. One is CO2 hydrogenation, really to address the CCUS and improve the energy efficiency by designing new type of catalysts. Second one, I'm going to talk about the Energy Earthstock Center, which you're looking at how you can electrify the chemical industry to decrease emissions. All right, so closing the carbon cycle. The recent Department of Energy Earthstock on clean fuel and products really urged that we need to close the carbon cycle. Essentially, all the fuel and chemicals we use are going to end up as CO2 in the atmosphere. We need to capture those or take them down, and then to convert those back to fuel and products to use. So doing closes this carbon cycle will help to decrease the use of fossil fuel, so that at least can significantly reduce the overall emission. Of course, this has not been practiced industrially because there are challenges there. So make CO2 into use for fuels and products. Typically, you need add hydrogen to it, right? Hydrocarbons. That's typically what we use, or oxygen. Typically, you need hydrogen. So those not only challenges CO2 difficult to actuate, but also challenge of make clean hydrogen. And also, when you look at CO2 hydrogenation, there are many reaction pathways you can go through. You can probably most mature one I would argue is methylation to make methane, but that's less desirable because they have a lot of methane available nowadays, natural gas. Really, you would like to use other, make other more valuable products, but you can see that those a lot of pathways competing there. It's really hard to make a highly selective to one type of product you want to use. And you can use just the methanol as one example, which you think is easy. But if you look at this is just one simple DFT calculation. I don't want to go into details, but I just want to show you how complex this reaction pathway can be by making CO2 hydrogenation to either CO or methane or methanol. And you have to competing all these different pathways to go there. So how do we approach this? Typically in catalysis, we're looking at supported metal catalyst. That means you have a metal species, which is gold here, supported on a support, which is black. So the support can have a significant role to impacting the property of the metal and catalyze the reaction. So to control the property of this metal center, there are many ways to do that. You can essentially using different metal or using different support as reviewed in this chart. So what we approach this a little differently is we look at support. Traditionally, most research has been looking at changing the identity of the support, meaning you change the cation. So you're looking at, for example, aluminum oxide, silicon oxide, or titanium oxide, you change the cation, but keep the oxide. And then you put a metal, for example, copper on top of it, which is typically good for CO2 conversion. But there's another space that can be explored, which you can change the anion, which has been really very few study has been done. You can think about you change the oxygen with nitrogen or carbon, and in this case, we would like to change it with hydrogen. or is hydride. What we start with is a pretty standard perovskite or complex oxide material, which is shown here as barium titanate. You can see that in the center, the green is barium, while in this octahedral center, light blue are the Ti atoms, and then the red ones are the oxygen. Through some chemical treatment, you can replace some of this oxygen with hydrogen, and you turn it into hydride. And to imbalance the charge, some of the labeling Ti will be reduced from Ti4+ to Ti3+. So you may make this material, and the good thing about this material is that it's just stable in air up to 400 Celsius. So you can handle very easily. And those perovskite material have been shown that you can enhance hydrogenation reactions by other groups. So what we have done with our collaboration on computational work with Jian Jiang at Vandenberg University is looking at computationally how this material behave under different conditions or for hydrogenation reactions. I'm not going into the details, but I just want to show you that the model tells us what are the structure are stable under different conditions. And the lattice hydride in those oxyhydride can participate in hydrogenation of ammonia and semi-hydrogenation or select hydrogenation of acetylene to ethylene. So based on those studies, we hypothesize that those hydride in the lattice can not only facilitate select hydrogenation of CO2, but also can impose electronic effect on supporting metal, in this case copper, so that it can affect the activation of CO2, but also stabilize or destabilize the intermediates to direct the reaction to the desired pathway. All right, let's show if that's the case. First, we have to make those samples. We make copper supported on barium titanate, we call BTO, or barium titanate oxyhydride, we call BTOH. Typically, use X-ray diffraction to tell the box structure. It's showing on the left. They are pretty much no change when you introduce some hydride. And then to quantify how much hydrogen in this material, you do a thermogravimetric analysis. Essentially, you hit the sample in oxygen to high temperature. The oxygen eventually will replace those hydrogen. Then you observe weight increase. From that, you can back calculate how much hydrogen you introduce in your lattice. And in this case, we show that we have 0.2 hydrogen out of 3 oxygen in the lattice. And then you can use neutron spectroscopy to really track the chemical identity of those hydride. And showing on the right is that you can see the Ti hydride bending mode. And even after reaction 250C 30 bar, those hydride are pretty much stable, telling you that those oxyhydride indeed are stable under CO2 hydrogenation condition. All right, we made those samples. Well, let's test them for CO2 hydrogenation. The reaction condition typically we use listed here 250C 30 bar, and we flow CO2 and hydrogen 1:3 ratio, and then we compare the copper on BTO versus copper on BTOH. You can see that the selectivity for CO blue bar drops, while the methanol selectivity increase. And same time, the activity also increase, so that you can get 3 times increase in the space-time yield for methanol. That's your desired product. So just by replacing some of the hydrogen in the support, you seem to get a 3 times increase in performance of desired product. And the stability test shows that the catalyst can be quite stable, at least our lab condition 100 hours. And the selectivity is a interesting switch between at the beginning, it's mostly set to CO, but then after 5 or 10 hours, stabilized to dominated by methanol. All right, so we saw those increase in methanol yield. Then the question is, are this really due to the hydride or due to the difference in copper, right? We know in catalyst, the size of nanoparticle can make a big difference. Then we want first to eliminate that the particle size are very similar on those 2 materials. And here shows indeed that's the case. If you look at microscopy, that before and after reaction of both catalysts, the copper particle size are very close, around 2 nanometer, not much change between the support and before and after reaction. And furthermore, you can do in situ or operando X-ray absorption spectroscopy, which we went to Stanford to do this under 250 C 20 bar, close to what we do at our reactor, and monitor the oxidation state of the copper species, as well as the coagulation status of those copper species. Essentially, not draw you to the details in the plots because you can't see the difference. That means all the two samples are very similar in oxidation state, close to metallic copper. Not surprising, this is a highly reducing condition. And then from the x-axis part, tell you that particle size are essentially the same. So all this tell us that the copper particle on the two different support, BTO, BTOH, they are essentially the same. So then we can confidently say the hydride is making the difference, right? Then the next we want to understand how does the hydride change the reaction pathways? How does it affect the kinetics? First thing we want to show you that those hydride indeed can participate in the reaction. We did a HD exchange experiment. Essentially what we do, we flow D2 over the sample without co-feeding hydrogen, and we see HD evolution with mass spectrometry. If you see HD coming out, that means the gaseous D2 can react with the lattice hydrogen to form HD. That's what we saw. At 250 C, you do see about 30% HD evolution, and then the rest evolve at much higher temperature. So telling you there are two types of hydride species that can be present in your catalyst. The small proportion actually can be active under your reaction condition. So then we want to see, can those actually react with CO2, right? So then what you do is we call CO2 temperature program reaction without co-feeding hydrogen. You flow CO2 under pressure condition. And then if there's any product coming out, it has to come from the hydride, not gas phase, because we don't have gas phase hydrogen. In this case, the mass spectrometry again, we saw methanol production, telling you that the hydride can hydrogenate CO2 to methanol. Then we went further. Can those vacancy created by the hydride reaction be refilled? And meaning, can those be catalytic? Then what we did after this step, we feed D2 again, and then we do another CO2 TPR, and we monitor deuterated methanol. We do see deuterated methanol coming out again. So what this tells you is a so-called multiplying carbonate mechanism that the lattice hydride can react with CO2 in addition to the surface hydrogen on the copper to hydrogenate methanol, to hydrogenate CO2 to methanol, and then be refilled by gas-phase hydrogen. So this actually makes the reaction kinetics different, as we showed that when you measure the reaction order of both CO2 and hydrogen. I want to focus just on hydrogen, which is on the top. The red one is for copper on BTO. You see the hydrogen reaction order is 1.5, while for the one on the copper BTO edge is close to 1 or 1.1. So there's a significant decrease in the dependence of hydrogen for this reaction. What it means is that on the surface of this copper BTO edge, they have more widely hydrogen available for catalyzing the reaction than the copper on BTO. So this, we believe, that's also related to the hydride on this catalyst, which can be more reactive for CO2 hydrogenation. All right, let's talk about intrinsic kinetics. When we talk about kinetics, we really care about the rate and the number of the sites. And when we talk about rate, we for catalysis, we really care about the true rates, which we call turnover density, meaning how fast your site can change your product to your reactant to your product per unit time. And to get that, typically there are ways you can count the sites, but what we use is a special technique we call the steady-state isotopic transient kinetic analysis, in which case we don't disturb the reaction, but just by doing isotopic exchange, we can derive back out the kinetic information on the reaction condition. So this is how it works. If you do a normal CO2 feed with hydrogen, you get argon, you get a methanol out by monitoring mass back, and then you can have another reaction gas pass. You can switch the valve to this labeled gas, and then in your mass back, you would see the labeled methanol coming out. And from this, you can derive your turnover frequency and the number of sites on your catalyst. Here's how we do it. All right, so in CO2 hydrogenation, we label this CO2 with carbon-13 CO2. It has very little kinetic isotopic effect because we tested that. And then from a normal switch, this is what you saw, the mass spectrometry tracer response. You always have this tracer, we call argon helium as a tracer. You see that they evolve first, and then you see your methanol coming out have a delayed time. This is because your methanol interact with the catalyst, has reabsorption, reinteraction, so that delayed its response to coming out of the reaction. Similarly, for the labeled products, you see helium come out first, and then you have labeled methanol come out later. So you can see that this is on copper BTO, this is on copper BTOH. The delay is actually different. And then what do you do to minimize those reabsorption, diffusion limitation? You increase the flow rate, you do different rate, flow rate, and then you extrapolate, you get the infinite flow rate time, where only you use the interaction between your material and the reactant, not the diffusion or the reabsorption. So that's giving you the intrinsic parameters of your kinetics. From those, you can calculate what's the surface density of the intermediate or the active site, as well as the turnover frequency, as I talked about a little bit earlier. So this table just compares the two catalysts. You can see that by introducing the lens hydride, it increased about 50% of the number of active sites on the surface, but also increased about 2 times the intrinsic rate, which is turnover frequency. So it's pretty significant. Then we would like to know how this actually impacts the reaction mechanism of pathways, where typically spectroscopy will play a role. And then you can combine the silica with FTIR, and then you observe what's happening on the surface and how you correlate surface information with the product information you get from silica. All right. So I'm showing here just a certain range of both catalysts. On the left on BTO, on the right called BTOH. All these peaks are due to formate. Okay, I just assigned that for you. The blue ones are before the switch, and the red one are after switch. Because of isotopic effect, the frequency will shift to lower frequency when you have heavier elements in the species. So you can see that on both surfaces, you see a shape of the formate peak, but the extent of this of the change is different on the two surfaces. And if you do a quantitative analysis of peak area integration, you can see that on the copper BTO surface, there are about 50% exchangeable formate. What that means is on this surface, you have half of the surface formate are spectators, another half are participating in a chemical reaction. While on the copper BTO edge, you have 90% are active, only 10% are inactive. Okay, so we can explain this again by the role of hydride, because from a DFT calculation, we put a copper cluster on BTO versus on BTO edge, and you calculate the D-band center of the copper cluster. You can see that the D-band center on for the copper on BTO edge decreased compared to those on the BTO. So what does that mean? When you have a D-band center decrease, meaning your surface reactivity of the metal is weakened. That weakening of the reactivity telling you that the bonding strength of your intermediate with the copper surface is less strongly bound, so that have better chance to turn over. That's what we observed here, that on those BTOH surface, actually you can have much more surface format can be turned over to your product. All right, so we show that this format are intermediates, and but the question is, are they the major intermediates? when we talk about that, we need to come back to the reactor, the rate, not just turnover frequency. As the rate is a function of turnover frequency and the number of sites. Can you get the rate out of spectroscopy? We have the time, right? The only thing we need is quantify those. So what we do is we do a standard, like a sodium formate. We impregnate those on those two samples. And we do a calibration curve, meaning how much area corresponding, how much more amount of formate on the surface. And then you can use that to back calculate in undirected condition, how much formate or turnover, and then you get the rate. And you compare that rate with your reactor rate to tell you if they are real infinity or not. All right, so showing on the right, the blue are the methanol formation rate from the reactor, the red is CL, while the green is the spectroscopy rate we observe directly on the surface. You can see, surprisingly, the green ones are much faster than the reactor rates, either CL or methanol. So what does that tell you? We think that the formate hydrogenation is easy. I mean, relatively easy compared to a later stage, which we cannot see spectroscopy. Maybe it's more difficult, it's a rate-limiting step, so that step we cannot see, but that limited really is the final rate. So this is what we can get out from this kind of quantitative spectroscopy analysis. All right. So let me briefly conclude this part by showing you that you can use line tuning of support really to impact a catalysis, in this case CO2 hydrogenation to methanol. And the hydride play two roles. They directly can participate in CO2 hydrogenation through a multiplying current mechanism, and indirectly they can help to destabilize some of the key surface intermediates that you give more reactive size for the CO2 hydrogenation. And that's a feature in this cover image of this journal. All right, so you wonder what's next, right? Obvious one, we want increase the content of the formate, the hydride in this material. So we showed you the 0.2 sample was in the middle, and then we increase that hydride content to 0.5. However, you don't see actually a performance increase from methanol, actually a little bit decrease. So then we think about this probably is actually quite reasonable, because I will show you that in Hg exchange, you have about 30% exchangeable. And reasonably is that those hydride, when you start making them, they probably first, because it's an exchange reaction, when you make those hydride by reacting with calcium hydride, then it's in solid state of a catalysis reaction. They start as an interface. So you would form those hydride on the surface first, and then subsurface, and then bulk. And then those bulk hydride really hard to move. Then you only have those, doesn't matter how much you make, you will have a very similar surface hydride or the subsurface hydride in your material. So that tells us really what we need to go next is really to increase the reactivity of those hydrides. Can you move that bulk hydride more reactive so that at low temperature, which is reaction temperature, in our case 250 C, you have more reactive hydride to participate in the reaction. Of course, further on, you can capitalize those hydride to really to do the coupling reaction for CO2 hydrogenation. And hopefully we can report those results in the near future on this slide. Okay, let's change gears. With less detailed research, but more on general on this ERC we just found last year, non-equilibrium energy transfer for efficient reactions. David Shaw is a director. The motivation for this center, really, I think I have already shown this, that the chemical industry is a big emitter and energy consumer. There need a way to address those. And those energy typically provided by burning fossil fuels that give you a lot of GHG emission. And this is particularly true for endothermic reaction, which shows here, basically, you need a high energy barrier to overcome to make your products. That typically needs a lot of energy input. We thought is, can we use electrification to decarbonize those chemical processes? And the hypothesis really is, can we use non-equilibrium approach? What we mean non-equilibrium is schematically showing here. Under typical reaction, we do at the equilibrium condition, you have a fixed temperature, fixed pressure, right? But if you can change the temperature as a function of time or the pressure as a function of time, now you have much broader space to explore for your chemical reaction. You can change the reactivity, you can change the selectivity. So this is really you can show here, if you drive up your reactant with the energy up at the energy landscape, under steady condition, it will draw to your ground state. So you get your typical product. But if you use the non-equilibrium, then they can pretty much stay in some of the metastable state by doing a transient temperature jump and fast increase, fast decrease, or pressure increase, pressure decrease, so that your reactant or intermediate can be trapped in some certain state. So really, our thought is using this fast temperature and pressure gradients to allow unconventional pathway to be realized with high energy and atomic efficient, so that we can really lower the GHG emission. And our approach using the pick-two approach, one is a programmable geoheating, and otherwise mechanical tasks. So before I go in, I want to give you a little bit of background on those two different approaches and how they might hold the promise to really drive chemical reaction with high efficiency. So I think we're all familiar with geoheating or resistive heating, the light bulb. But what we like to do is a little bit different. This is a steady state operation. We'd like to do a programmable, meaning pulsed operation. You can pulse your current through the your heating material, and depends on the thermal inertia of your material. Typically, we choose high thermal inertia material so that you can jump temperature very fast, 10 to 5 K, 6 power K per second, and then you can hold the current for a very short time, milliseconds or 2 seconds. And then once you withdraw the current, your temperature will drop very fast. So through this operation, you can see that by here how you can change the reaction selectivity. Let's say you have two products, A and B. A happens at a very short time scale. B happens at a longer time scale. So what you do is you keep your temperature profile at very short scale, matches A, but then you cool it down. Then B will be accessible from this profile. Then you can manipulate your chemical selectivity. And because of this temperature, you can rise pretty high, then the thermodynamic limitation or kinetic limitation can be overcome. So you could have high rate and high selectivity through this kind of operation. Let me just give you one specific example how this works. We look at the method, this is reported in one of co-PIs. Previously, if they look at the methane pyrolysis, which is a way to make hydrogen, but then the carbon typically goes to solid carbon. And what they used here is a carbon felt or carbon film. You collect with the two contact, and then you apply your current. You can heat up very fast to very high temperature. And this is just a schematic to show how this thing works. You have this heater inside a tube, you flow a gas, and then you can operate at millisecond time scale, and then you cool down, you have some gap, and then do another pause, and then you can drive the reaction. And this, you see, you can play this video. All right, so that's in the lab, how this thing operates. You can see the flash, meaning you're applying current, and this thing hit fast, cool fast. So the performance-wise, you can compare that with traditional operation, which is showing here. You can see that majority make is coke and some other large compound. of course, enriched with hydrogen. But with dual heating, you can see that majority of products now is C2 products. So why is that? Because the formation of C2 is pretty fast in the time scale of milliseconds. But from coke, which is a polymerization reaction, it takes time. The modeling shows that you need a few seconds to make coke. So then if you don't hold the temperature high long enough at the high temperature, you can essentially quench the coke formation process, but only favor the products which happens at a short time scale. So that's where you made this a lot of C2s. And they compare this with other catalysts. Actually, you can see that the performance at the very top. And also this one only uses carbon, no catalyst, right? So just carbon heated up. So there's potential you can incorporate catalysts, which we in the central do to further, to save the energy. You don't need to have very high temperature, but still be able to do this kind of selectivity control. And later on, this was also showed that you can do solid-solid type of reaction. For example, plastic upcycling. Then you can have a plastic in contact with this carbon field. You have this pulse heat. You have to decompose them back to monomer more efficiently than traditional sensitive heating. All right. So another one, mechanical catalysis. I'm sure most of us have heard about ball mills, right? This typically was used to make materials, synthesized materials. But only recently we realized that this can also be used as a way to catalyze chemical reactions, because when the ball hits the material, it can have a lot of effect. So let's see. This is a video. I'm not sure if I can play it. Is this? Let me change my pointer back to. Yeah, I can't play it. But anyway, this is a high-speed camera, shows how the ball moves in a ball mill, and from that you can see how fast the contact of the ball with the vessel and the material. And essentially, in this case, we used a calcium carbonate as a model study to decompose it to calcium oxide and CO2. So dynamically, it is about 800 C to have this reaction happen. Basically, you want to decompose, you need 800 C. And using this ball mill, actually, this reaction can be driven. You can see that depends on your milling frequency, the rate can change. So this basically tells us the temperature hotspot, or we call hotspot, when you ball heat the material, the hotspot can be very high, and that can reach out to more than 800 C. Otherwise, this reaction cannot happen. Or could be some other combined effect. And the collision of the sample, of the ball with the sample, is a time scale from that fast movie is of microseconds to milliseconds. All right, so this is really again another non-equilibrium transit approach to drive reactions. And let me just give you two examples how this drive chemical reactions. One is ammonia synthesis. This is solid gas interaction, where you can see that in the vessel, titanium powder, the stainless steel ball, and you flow hydrogen nitrogen, and you just shake it. And then you start seeing ammonia coming out. So this is normally the vessel is only get about 50 Celsius. Traditional ammonia synthesis typically is 400 C, 200 bar condition. This one, almost ambient condition. You just solute the ball, you can get ammonia synthesis out. And the rate is very high. And mechanism-wise, it was found out that actually during the ball mill, the titanium powder actually be nitrated by the nitrogen, and then the hydrogen react with the nitride, ammonia, and then those titanium powder hydrated again by nitrogen. So it's, again, this so-called redox mechanism occurring in those ball mill processes. So another case is a solid. Again, you can use ball mill to grind solid materials. That's typically for material synthesis, right? In this case, you can do polymer decomposition. In this example shows a PET particle in that you can grind and decompose back to the monomer very efficiently with the ball mill. Okay, so by showing you this two approach, clearly you can see there's a commonality between these two approach. That is the transient temperature pulse or the hotspot, right? So in the programmable dual heating, you can get a high pulse out temperature on your material. While on the mechanical glass, you can also through the collision, you can have very short time hotspot. So those actually the reason we pick those two approaches together, right? That one can be used benchmark to help understand the other. And furthermore, those approach actually has been demonstrated can be scaled up. For the resistive heating, this is demonstration in UK. It uses resistive heating for environmental remediation. And on the right, it shows the ball mill actually applied in industry for cement production at 1 million ton per year scale. So those approaches are possible to apply at the industry scale. However, has not been demonstrated for chemical reactions. This is really because there's a lack of fundamental understanding how this line equivalent energy transfer mechanism works and how they help to drive chemical reactions. And that's why we established this center. And some of the key challenges in this center we really like to answer are including how can we explore this transient temperature pressure gradients and those metastable structure when you apply those to the material from the local heating event to control chemical reactivity and selectivity. Second, how can we focus on non-equivalent energy transfer at a spatial and temporal resolution to accelerate chemical reactivity and minimize the energy loss? Thirdly, can we understand those chemical reactive structure created by this line stimulation and make use of that to further improve your chemical reactions? So this is the mission statement based on those these challenges in those two line approach. We really would like to understand and control spatial and temporal line heat transfer to achieve energy and atom efficiency in electrified process for catalysis of endothermic chemical reactions, so that it can go beyond the limitation of thermodynamics and kinetics, eventually to help to decarbonize US chemical industry. And that's the central main non-equivalent energy transfer for efficient reaction or liter. And this is just schematic shows the structure of the center. We have 3 slots, 2 experiments and 1 modeling, really to combine them together to drive the efficiency of this electrification. And we pick 2 prototype reactions to really test our hypothesis in the center. We look at 2 extremes of the molecules. One is that light acting small molecule C1 to C3, and the other one is at the very end long chain hydrocarbon or plastics. So we're looking at breaking the CC or CH bond, those typical endothermic reaction. We would like to use this approach to really learn how to use long-term energy transfer to make those useful monomer, olefins, or hydrogen through those reactions. And the interface, we're looking at a variety of interfaces that generally practiced at the chemical industries. So a little bit more on this research slots. Really, we'd like to understand how the energy transfer occurs in those transient temperature and pressure, and how the reaction occurs, chemical kinetics and mechanisms, how they are different from equilibrium normal steady state operation. And a lot of efforts in this actually is to develop model apparatus to really understand them, because all this are at a very fast time scale, spatial resolution, traditional approach to understand really not working or smart work. So we each of the case we're trying to develop some model instrumentation, model reaction, and to help understand this. And also, of course, we collaborate with the Oscar domain to really use multi-scale modeling to really derive the efficient surrogate models that can be used to control this electrification process, because there are a lot of parameters you can explore, so that we can use this surrogate model. You hope to get a higher efficiency for those electrification processes. And this is just a structure of the center. It says David Schultz leading this center. I'm the deputy director. We have 3 SROS spread out, SROS leaders spread out ORL and outside. We have about 8 institutions, 27 PIs. This is a 4-year project funded by BES and Oscar. Let me just use one slide to tell you what we're working now, because I'm all talking about pretty much like a proposal. What we're working now is we call it a jump start project to really to help to to bring all the PIs together to work on a big project. This is seemingly a simple project. What we're looking at is based on one simple hypothesis. We talk about hotspot a lot, right? Our simple hypothesis is that the hotspot due to collision in mechanical capacity cannot be sole reason for the performance it can exhibit it. There must be something else going on. So what we trying to test is using geoheating as a clear benchmark, because in geoheating only temperature effect, right? We compare the same catalyst, the same reaction with mechanical gas and geoheating. We picked up propane dehydration, a simple experiment reaction. You can go to propane to propylene and hydrogen, or you can go to hydrogenolysis to C1, C2 products. So I don't have results shown here. We have done some preliminary data shows that both approaches can very efficiently catalyze this reaction, but the selectivity is very different. But still trying to understand it. But the key is really to show you what we're working on, how we get the team going together with one seemingly simple but very complex underlying mechanism driving the reaction with those very different approach. And of course, for the mechanical class, as I said, we have to develop a model apparatus to understanding. Because if you think about it, the ball mill is moving all around. How do you characterize this? This is a significant challenge, right? So there's no way, almost no way to understand it. So what we do is we develop we call it a single impact or repeating impact apparatus. Basically, it's very simple. Use a piston, almost like piston structure. You have a ball at the bottom, and then you can control that with a valve to control it and to heat your sample at the bottom repeatedly on the same spot. And you can control the energy of this ball to mimic what's happening in a vessel. And then this box you can enclose with an optical window. You can take it to X-ray synchrotron to study, or use an ultra-fast laser spectroscopy study at Oak Ridge. And we hope to use this to really understand what's the transient structure look like under this stimulation of the ball, and what's the surface chemistry occur, and how does that compare with the steady state operation. So this gives you some idea, really how the non-equilibrium approach can drive chemical reactions. Of course, there's a lot of potential impact from this research. I think fundamentally, personally, I think if we can carry out this research with all this team together, really get a fundamental understanding of how this non-equilibrium at fast time scale and high resolution, how this energy can be used to catalyze chemical reaction, and what's the difference in the kinetics and mechanisms of this chemical reactions compared to operation on a steady state, that's very significant. Of course, if it's very successful, this could lead to advanced, really distributed modular electrified processes to making chemicals using the renewable electricity. Okay, I think I'm at the end. I'd like to ask to acknowledge the group, the folks have done some of the work as shared here. And of course, our collaborator and the funding from Department of Energy and a lot of the user facility, both at ORL as well as at the synchrotron resource. Last but not least, we are hosting the next North American Catalysis meeting in Atlanta next year. It's 11/29, and the Southeast Catalysis Society is taking care of this meeting. It's next June. If you're interested, and take a look at this. With that, I'm done, and I'm happy to take any question you have.
Let's talk that. Very tight stories. Wonderful. Questions?
I understand your objective is to decrease CO2 emissions in industrial chemical processes. And I saw an example of making of ammonia, making cement, making plastics. What are some of the other primary high volume chemical processes, or components that we might be more, we might be familiar with that your research might have an effect on?
Yeah, so this the ERC, we're primarily addressing the industry heat, right? So we look at chemical processes, but also you're right, other non-chemical processes like a steel, for example, a steel plant. That's a few percent, I think, overall CO2 emission. That's where you can make a significant impact by use hydrogen instead of using traditional fossil fuel to heat this up to high temperature. Another one is the cement production. Of course, that as shown in the ball mill is really just crank the minerals, but not really for the later stage. So those are the big emitters. Not necessarily to be addressed by our approach. We are really focused on the chemical reaction side.
I understand, but what are the high volume chemicals and the chemistry and industry that your work might have an impact on? That we can relate to. Okay, where might this be applied? Let's put it that way.
Okay, yeah. So of course, ammonia synthesis. Ammonia is a big one. Actually, it's more related to hydrogen, not the real ammonia itself. Is hydrogen production is a big emitter there. And another one we show there is natural gas, which used to make olefin, which is precursor for plastics. That's also a big one. We choose that has some reasoning there. So yeah, I would say this is really to show that you can use this new approach to address some of the chemical reactions, but some other heavier, larger processes could potentially benefit it. DOE actually has a list of 50 chemicals that has heavy impact on CO2 emission. There's this ammonia, of course, there, methanol there, olefin like propylene, ethylene are all there. Yeah. So we touch some of those.
Thank you. Ellen?
This is beyond the scope of your lab research, obviously, but what are the challenges in scaling this up for large industry application?
So I think that's a very great question. For the electrification, I show that there are some industry scale use. But for chemical reaction to scale up, typically there are a lot of challenges. Is when you scale up things, the performance will follow. There are a lot of mass transfer, heat transfer, reactor design. All this thing has to be taken consider for us, we are focused on catalyst, right? But to take this to the market, really, we need a lot of other expertise to work on it. I don't know, we have all this expertise actually. Like for example, in chemical process group, they intentionally build the scale of small lab scale. We typically for catalyst we use less gram. What they're looking at using 1 kilogram material catalyst, then the reactor volume is much larger. So we're looking at 100 times, 1,000 times increase. So there are a lot of challenges there. They have a lot of modelers looking at the reactor scale, how the mass transfer, heat transfer impacted performance. Then you look at that next scale. Yeah, I'm not particularly familiar with those, but I know there's a lot of challenges in addition to catalyst.
Okay, thanks.
Sort of following that up, you showed this UK thing. I can envision a filament heating up very quickly and dropping very quickly. But on a scaled up basis, the heat transfer and everything like that, I can't envision something industrial reactor size being able to flash like that and cool like that. How conceivably would that work?
There was a science paper actually a few years back for the resistive heating. They did some modeling, shows that because of heat distribution in the dual heating is much even than the traditional, heat. You heat the outside and the center of your reactor, there's temperature drop gradients, big gradients. For the dual heating, because it directly heating your catalyst with current, then there's very little temperature drop. What the model shows that for the same amount of production, you need much smaller scale of unit to get the same productivity because of that and some other reason. A lot of engineering sense there that you don't need to go to industry scale. That's why I say the impact is modular. We're looking at more modular processes. Yeah, I think.
Right.
I didn't get a clear picture of the opposite process of dehydrogenation. What is it and where is that used? I got no picture of that in your presentation.
Dehydrogenation?
Yes,
Okay.
the opposite thing. You're doing the other way around. You're getting rid of that.
Yeah. So dehydrogenation, this is actually commercially processes now for making olefin.
Thinking what?
Olefin. For example, propane use propylene, ethane make ethylene. Those are the monomers you can use to make plastics. Yeah, so it's a heavy, big market out there. Yeah.
I'm not a chemist.
So use plastics, right? Plastic start with small molecules, then you collecting together, make a big molecule. That's what your plastic is. But this you need some precursor, and that's a reaction to make the precursor.
In your mechanochemistry, where the ball slams into a catalyst, I think you're right. There's much more going on than just a temperature drop, temperature increase.
Yeah.
When you fracture oxides, you get triple emission, which is a mixture of very energetic electrons and photons that come out from breaking bonds. And these hot electrons could generate new selectivities in some of your reactions. That could be a major contribution to the reaction. I think it'd be very interesting to look for selectivity changes in reactions, especially if you can anticipate which ones may lead to where free radicals may be a reactant.
Yeah. I think I have a slide in the back shows what all the potential contributor in mechano catalysis, hotspot, piezoelectric, quite some other effects that can be there. And to isolate each of them, there are some ways you can do it. Basically, you can choose different materials, right? Soft, heavy, inert, reactive. So there are so many you can explore and to understand. So I that's why we say hotspot cannot just one of it. Yeah. Yeah.
So in the barium nitrate example, you showed that it's easy to make formate and it's hard to make methanol, but you never said what happens to the CO. because you're partitioning. So, okay, you get this, how do you, can you tease out the mechanistic steps that take you to CO versus that, so you can push your selectivity more and more to methanol?
I know you're gonna ask. It's a great question, Phil. So I think I have not shown you is what we believe spectroscopically, the format goes to methanol. Because when we do the switch, we see methanol format goes down, we see methoxy goes up. They're proportional, but not CO. CO, which we have not spectroscopically observed, but we do believe it goes through different intermediate, which is a carbox format is HCOO, right? We believe CO goes through COOH, carboxyl whatever intermediate. But that one is not stable. It's hard to observe.
If you just feed CO into your reactor.
Yeah. So we have not done that. That's something we've always wanted to do. Typically in other like in the commercial catalysts, zinc, copper, zinc, aluminum catalysts, right? If you feed CO2 versus just a CO, the performance is very different. So they definitely, although they both can get methanol, but the pathway is not like CO2 go to CO and then go to methanol. That we believe is a direct pathway go to methanol. Yeah.
Okay, there's, I think we should thank our speaker one more time. Speaking to us, we thank you to the Friends of Ornell Coffee House. So